Assalamualaikum class and a very good day. Today we're going to learn about chapter 1.4 Mechanical and Physical Properties of Material. In this chapter, it will explain about two types of material properties. The properties of a materials is divided into two types, which is mechanical and physical properties. Three types of mechanical properties that we're going to learn today is tensile, hardness, and toughness. For tensile strength, we will learn about the yield strength and Young modulus, and their ductility and brittleness. The physical properties are things that you can see with your eyes, such as the material are solid at room temperature and may be opaque or transparent. First, we will learn about the physical properties. Physical properties are properties that can be seen or felt physically. It is actually the characteristic that responds of material to the form of energy. For example, such as heat, light, electricity, and magnetism. The example of physical properties of metal are based on their appearances, either opaque, shiny, silver, or colorful, density, solid at room temperature, they can conduct heat and electricity, they will reflect light when polished, and they will expand when heated or contracted when cooled. Here are examples of physical properties. As you can see, these are an aluminum oxide in three conditions. The first one is transparent, the center is translucent, and the third one is opaque. These are examples of physical properties of one material with different physical appearances. Now, we will learn about the mechanical properties of the material. Mechanical properties are the characteristic of the dimensional changes in response to applied internal and external mechanical force. For example, shear strength, toughness, stiffness, and many more. As shown in the slide are some examples of mechanical properties of a material. First, we will learn about the tensile properties. Tensile properties represented the strength of a material. It is conducted by pulling it in opposite direction. The tensile properties will be plotted to a stress-strain diagram. And the maximum value of tensile strength, or formerly known as ultimate tensile strength, will be recorded right before the material breaks or fracture. The unit that we usually use is megapascal. Shown here are examples of tensile specimen. Tensile specimen usually are in round shape with certain length. In the right, you can see the tensile machine. The specimen will be placed in the center. The load cell will determine how much load can the specimen withstand, and the extensometer will record the distance. This specimen will be pulled in an opposite direction until it is break. Here are examples of tensile machine available in the market and tensile specimen. The tensile stress and engineering strain are two formulas that are used in determining the tensile strength of the material. As you can see, the stress has a unit of Newton per meter cube and the strain is dimensionless. As a result of the test is the stress-strain diagram. In the stress-strain diagram, we have the elastic region. At the elastic region, If the material stops in the elastic region, it will return back to the original position. Next is the plastic region. It is where the material becomes ductile and will be longer than its original position. Then, at point 3 up onward, there are strain hardening. It is the part where necking happens. And lastly, point number 5 is where the fracture or break happens. Here are the examples of the stress strain formula and the explanation about strain hardening. This diagram is used to determine how the material will react under certain load. As you can see, this is how the material reacts at elastic behavior, plastic behavior, necking, and lastly when it's fractured. Here are some important mechanical properties from a tensile test. The first one is Young modulus. It is the slope of a linear portion of the stress-strain curve. The second one is yield strength. It is the value of stress at the yield point, and it is usually calculated by plotting the Young modulus at the specific percentage of an offset. Usually, the offset that we use is 0.2%. Next one is ultimate tensile strength. This is the highest value of stress on the stress-strain curve. And lastly, the percent elongation or ductility. This is the change in the gauge length divided by the original gauge length. Here are the Young modulus comparison of metal, ceramic, graphite, polymer, and composite. As you can see, ceramic have higher modulus compared to metal, and polymer have the lowest modulus compared to all other material. Here are the yield strength of all materials such as metal, graphite, ceramic, semiconductors, polymers, and composite. Here is what actually happened during the tensile test. At the first stage, where is the elastic stage, this is how the atom look like. And then at the elastic plastic stage, the atom will dislocate and slip due to larger stress applied. And lastly, before it fractured or before the permanent plastic after load is removed, okay, the material or the atom will permanently dislocate and break. So as you can see, here are the elastic deformation of initial, small load, and after is unload. At elastic deformation, after you unloading the stress, it will return to the original or initial stage. However, at plastic deformation, this is how it looks like at initial stage, and after small load is applied, the bond will stretch and the plane will share, and lastly, after it's unloaded, the plane will still share. It will not return to the original condition or location. This is known as permanent deformation. Permanent deformation for metal is accomplished by means of a process called slip, where it involves the motion of dislocation as you seen in the slide before. Most structures are designed to ensure that only elastic deformation will result when stress is applied. However, a structure that has plastically deformed or experienced permanent changes in shape may not be capable of functioning as it needed. This is the polymer change before it is undergo the plastic deformation, and then when you pull it in the opposite direction, it will cause necking, and what happened, the tangle polymer change will become a line. It will become a straight line due to the deformation. Thus, this makes the strength of the polymer increase. Here are tensile strength comparison. As you can see, of course, steel, titanium, or alloy steel has the highest tensile strength compared to other material. Another properties from tensile test is ductility or percentage of elongation. Ductility is a measure of plastic deformation that has been sustained at fracture. So generally, according to this graph, this material has smaller elongation but higher tensile strength. But the second material, the green one, has lower tensile strength, as you can see, according to the value here, the stress, but higher strain or elongation. So how do you calculate the percentage of ductility or elongation? Is generally by knowing the final length and the original length. So the final length minus original length over the original length times 100, then you can get the percentage of elongation or the area of elongation. Now let us move on to the next mechanical properties, which is toughness. Toughness is the ability to absorb energy up to fracture. A tough material usually have high strength and high ductility, a combination of both. And how do you measure the toughness? It is actually the area under stress-strain curve. Toughness is also defined as an energy to break a unit volume of a material. Look at this graph. Ceramic have smaller toughness because they have small area below the stress-strain curve. Metal have larger toughness because it has higher area. And polymer also has smaller toughness because it has smaller area under the stress-strain curve. So from this graph, we can also determine whether the material is brittle or ductile. If the material is brittle, meaning to say it has shorter length of strain. If the material is ductile, meaning to say it has higher length of strain. Different from metal, here are the stress-strain behavior of elastomer or rubber and plastic. As you can see, it will increase a little bit and then decrease and increase again before it breaks. So what happened is, initially, the amorphous change are linked and heavily cross-linked. And then, what happened is the plastic failure. During this stage, for elastomer, the deformation will be reversible. It will reverse back and then pull back before all the change are straight. and straight crosslink, and then after it all becomes straight, it will break. So the stress strain behavior of elastomer has two types, which is brittle response, a line chain, crosslink, and network cases. So here are the type of plastic and elastomer involved, and plastic response. One is for semi-crystalline case. Now we move on to another properties that we can obtain from tensile tests, which is fracture mechanism of a metal. Metal can fail either by brittle or ductile fracture. Ductile fracture is better than brittle fracture because ductile fracture will occur under a certain period of time, but brittle fracture is fast and it can occur with flaws at lower stress level than ductile fractures. So, as I have mentioned before, this is the type of ductile and brittle fracture. So, this is the original shape of the specimen. This is the brittle fracture. It happened without any necking and very immediate. And this is ductile fracture. It happened with the necking. After the necking, then the material will break. Okay. So, which one of these is ductile and which one of these are brittle? Okay, please answer me. Okay, you can answer which one is ductile, either the left one or the right one. For the answer, this one is ductile fracture and this one is the brittle fracture. Due to the nature, as you can see, this one has undergone necking process before it fracture or break. But this one, it become flat. Okay, same as the diagram here. For ductile fracture, localized deformation of a ductile material during a tensile test will produce a necking region. Okay, so this image show, okay, before it fracture, it will undergo necking process first. It will slowly become smaller. The diameter will become smaller before it eventually break. Okay, this is example of examination question that will come or have that always come out in the exam. Okay, the first one is ductility is one of the most important mechanical properties. So, first, define the ductility of a metal, and second one, with the aid of schematic diagram, describe elasticity, elastic and plastic deformation. So, here are the answers. Ductility is one of the mechanical properties, and it is the ability of the material to have large plastic deformation before fracture, or it can also be defined as area under plastic deformation in the stress strain diagram. As for elastic deformation, we all know that in elastic deformation, all the atom will return to the original stage. So what you do is you have to construct three diagrams. The first one is the initial stage, and then after the small load is applied, and after the stress is unload. But the initial diagram and after the stress unload are the same. Okay. So for elastic deformation, it is a deformation that is non-permanent or reversible. It can be reversed. It can be returned to the original position. In terms of the atomic level, the bonding between atoms are stretched and it will return back to its original shape after the force is released. For plastic deformation, different from elastic, it will not return to the original stage. and the deformation is permanent. In terms of the atomic level, the bonding between the atom will break and the atom bonded with new atom. As a result, it causes permanent deformation. So generally, this is how the atom look like at original stage, and when you apply small load, two types of deformation occurs, which is elastic and plastic. So for this part and this part, it will stay elastic, it will return back to the original position. But for this, the part in the middle, the bond will stretch. Okay, the bonding will stretch and cause a plane shearing. Okay, and after unload the stress, the plane still shed and it will not return to the original position. Another popular question is, what are the difference between ductile fracture and brittle fracture? So we all know that in ductile fracture, plastic deformation occurs, and in brittle fracture, small or no plastic deformation occurs. In ductile fracture, high energy absorption before fracture, and in brittle fracture, low energy absorption before fracture. Ductile fracture were characterized by slow crack propagation, meaning to say it will break slowly, and brittle fracture characterized by rapid crack propagation. Ductile fracture has detectable failure, and brittle fractures have unexpected failure. Example of ductile fracture is metal and polymer, and example of brittle fracture is ceramic and polymer. And lastly, in the mechanical properties, we will learn about hardness of material. Hardness test is used to measure the resistance of material to penetrate by a sharp object. We have a few types of hardness tests. The first one is macro hardness. It is actually representing the overall bulk hardness of material, and it is measured using load more than 2 Newton. Then we have micro hardness. The hardness of material typically measured by using load less than 2 Newton, such as Knoop test. And lastly, we have nano hardness. The hardness of material were measured at 1 to 10 nanometer length scale using extremely small forces. Hardness is measure of a material resistant to localized plastic deformation. This plastic deformation is caused by a small dent or scratch on top of the surface of a material. Quantitative hardness technique has been developed where a small indenter is forced into the surface of the material. The depth or the size of indentation is then measured, and it will have a corresponding to some hardness number. The softer the material, the larger and deeper the indentation. Thus, the lower the hardness number. Now, let us look at how hardness works. As I have mentioned before, hardness is the resistance to permanently indenting surface. So you have a surface here, and then you have your indenter. In this case, the indenter is a small ball. It might be steel, it might be titanium, okay? So the size of the ball is 10 mm in sphere shape. So imagine when you indent, when you force this ball on top of the material, okay, on the surface of the material, it will leave a mark. Okay, so you have this mark over here, a hole, okay, on top of the material. So what you do, okay, you will calculate or measure, okay, the diameter of the indentation. The smaller indentation, meaning this material have higher or larger hardness. It is not significantly affected by the indentation of the steel ball. But if it has larger area, okay, they are they are being the area of the ball leaf is big, okay, or deeper. It means that the material is softer. So example here, there are the material with the increment of hardness, and of course diamond is the hardest material in the world, okay, and that's why there are some saying that say diamonds are forever, okay. And of course, as you can see here, most plastic are softer in terms of hardness. Here are examples of hardness tester available in the market today. We have a few different, and these are the indenter lah. Okay, and this indenter will move downward and give some force, okay, on top of the material, and after the force is unloaded, it will leave a mark on top of the material. Okay, why you have different type of hardness? Of course, because different type of hardness have different shape of indentation and has different type of load. For example, okay, there are a few types of tests available in the market. We have Brinell. For Brinell, the indenter is actually 10 millimeter steel, and this is the shape of indentation. It is actually spear in shape. And Vickers, it has diamond pyramid, and it is in the shape of the pyramid over here. And Noob, okay, also diamond pyramid, but different from the Vickers. Okay, the Noob actually has different type of diamond shape. And lastly, we have Rockwell. Rockwell that has different grade. For ACD grade, we have diamond cone, and for BFG grade and E grade, we have spear steel. So what are the difference between this? It's actually the load that can be applied, okay, to the hardness test. So some material, okay, can withstand only 5 kilogram. So if the material, okay, can withstand only 5 kilogram, what type of hardness indenter or hardness test, okay, will you use? Of course, you will use the Noob test. Look at the table here. It can only withstand 5 kilogram of load. But if you want a material that can withstand 3,000 kilo, so you will use the Brinell test. So how you choose your test hardness tester is depending on the load lah. The harder the material, for harder material, you can use Brinell, Vickers, and also some grade of Rockwell. But for lower one, you can use micro Vickers or Noob. Okay, so and how you actually determine the hardness number? Here are some of the formula. Okay, here are the hardness scale. Okay, for Rockwell hardness. Okay, again lah, I think it's quite the same with the one that I've mentioned before. But this one, okay, is actually you can look at the application or what type of material that you can use. Okay. Now, let us take a look at the indentation geometry for Brinell testing. Once you indent, what will happen is all the atom over here will dislocate. Okay, they will move from the original position. Okay, and this is how it looks like. Although you apply the load, okay, over here, what happens is all the atom will move and dislocate until it reach an area where it can withstand the hardness and we will not move. Okay, which is this area lah, kan? Up to here is the area where it does not move from the original position. Okay, what happens if you have only one type of tester? But, okay, unfortunately, you want the standard or you want the unit, okay, at different hardness tester. So we use the hardness conversion scale. For example, okay, for anneal my steel over here, okay, the value is 150 HB. This one if you use Brinell. But the same material, okay, if you use HB because over here, it is actually, okay, more or less 150 HV. If you use HRA, it is 50 HRA or 80 HRB, okay, none of it in the HRC, okay, because HRC is such a strong, is for stronger material, okay. So that is where we use the conversion table, because, okay, not every country, okay, accepted, some country only accepted certain standard. So we use this conversion table according to the standard in the country itself. Okay, so this is also the conversion hardness scale between Noob, Brinell, Rockwell, and then other types of hardness. So actually, there are correlation between the hardness and tensile strength. Okay, both hardness and tensile strength are the indicators of metal resistant to plastic deformation. So generally, as you look at the graph, the higher the tensile strength, actually the higher the hardness number. It is proportionately together. So lagi kuat material tu sebenarnya lagi keras lah dia. Okay, usually it goes around like that. Okay. So here are some example of the question exam, the question in the final exam. Hardness is one of the 4 important mechanical properties in engineering. Describe 4 types of hardness measurement method in terms of name and the indenter. Here are the answer. Okay, for the answer, I shall ask you to submit it to me and show me in the next class. Okay, so please verify, okay, or give answer to the question about hardness. Okay, so as a summary, okay, we shall recall back what we have learned today. Stress and strain, okay, is actually size-dependent measurement of load and displacement. Okay, so usually the higher the stress, the longer the strain. Elastic behavior or the reversible behavior that is often shown in a line relation between stress and strain. Okay, it is the first region in the stress strain curve. And plastic behavior, after the elastic region, the material will undergo plastic behavior. This permanent deformation behavior will occur only when the tensile or compression uniaxial stress reach stress of Y. Okay. So this one, it occurs, and in the plastic behavior is where the plastic deformation occurs it will not return to the original stage because of the slip of the plane. Okay. Toughness is the energy needed to break a volume of in unit volume of a material. And ductility is the plastic strain at the failure. And lastly, for today class, I shall ask you to answer these questions. The first one, list 2 types of physical properties of a material. Number 2, what are the 4 main properties and tensile tests? Let me give you a hint. One of it is ductility. Number 3, what is toughness? Number 4, what is hardness? And number 5, list 3 types of hardness and their differences. That's all for today class. Thank you so much for your attention and see you in the next class. Assalamualaikum.